Thank you so much, Megan, and it is a treat indeed to be here this evening. Thank you all for coming out and listening in and being a part of this evening's activities. Please know you're welcome, and we're really excited to have you here this evening for our Out Loud lecture series. For those of you new to these events, each Out Loud lecture is inspired by the innovative work of Argonne researchers and led by them. So you get to see them firsthand and have conversation with them firsthand this evening, which is very exciting. These events are designed really to bring everyone into the conversation and to make science accessible and engaging. So I hope you find that true this evening. This year, our Out Loud forums are especially meaningful. We are celebrating two important milestones. One Megan highlighted, Argonne's 80th anniversary. Can you believe that? 80 years here in the midst of, here in the midst of DuPage County Forest Preserve, certainly Waterfall Glen Forest Preserve, DuPage County, I should say, really exciting for us. And also America's 250th birthday. Throughout this anniversary year, and especially at our Out Louds, we will recognize the impact of our people and their work, both past and present. For 8 decades, Argonne has driven pivotal discoveries, fostered dynamic partnerships, and delivered transformational science at scale. Science at scale means bringing together powerful tools, vast data, and broad partnerships to address complex challenges that are too large for any single team or institution to tackle alone. And science at scale is what we are focusing on this evening. Much of this work takes place at our research facilities, or what we call our user facilities. At these facilities, we achieve breakthroughs that touch our everyday lives in remarkable ways. By leveraging cutting-edge tools and instruments, we unlock new frontiers in numerous ways, from transportation and cybersecurity to advanced energy technologies. Our user facilities build on Argonne's legacy of transformational innovations. The work done here accelerates the science and technology that drive U.S. prosperity and security. With our talented researchers, collaborate with the broader scientific community at these facilities, they ensure that Argonne remains a beacon of scientific excellence for decades to come. Before we dive into tonight's topic, I also want to invite you to join us for a very special event. Please save the date for our open house on Saturday, June 27th. Like our Out Loud lecture series, this year's open house will celebrate Argonne's 80th anniversary. This free community event is a wonderful opportunity for family, friends, and neighbors to explore the world-changing science being done at the laboratory. Certainly, for more detail, scan the QR code on the screen, and it will take you to our official open house website, where you can sign up to be notified as registration opens. So we do hope you'll join us. Last time we had a sellout crowd, and it sold out rather quickly in a matter of just a few days. So 10,000 people. So please jump right in and sign up as quickly as you possibly can to make sure that we've got space for you. So it would be a real pleasure to celebrate 8 decades of Argonne scientific impact with all of you. And now we're going to turn to tonight's program to tell us more about why our user facilities are so important for society. We turn to Sean Jones, Argonne's Deputy Laboratory Director for Science and Technology. Sean serves as the Chief Research Officer and our Senior Science Strategist and Advisor. He oversees 21 research divisions, over 1,500 researchers and technical staff, and 6 national scientific user facilities, which is exactly what we'll be talking about this evening. So please help me welcome to the stage tonight moderator, Sean Jones. Please, Sean.
Well, thank you very much, Paul. It's a pleasure to be here with you tonight and to join you on stage to talk a little bit about our science and how we enable science. So some of you may be wondering, what exactly is a user facility? User facilities provide access to specialized instruments, tools, data, and staff expertise, which are all at the forefront of science and technology. Argonne has housed user facilities for decades. Our first user facility was the Zero Gradient Synchrotron, or ZGS for short, which opened in 1963. It was the nation's first proton accelerator, used primarily to study fundamental particle physics. Since the ZGS, Argonne's user facilities have been open to the global science community free of charge, as long as they agree to publicly publish their findings. That way, our discoveries compound and lay the foundation for decades of subsequent advances for society. This is extraordinarily beneficial for everyone. That's why researchers and experts from all around the world, representing universities and industry, have had a standing invitation to work at our user facilities. Each year, more than 8,000 guest researchers take us up on the offer and visit Argonne to use our cutting-edge tools and instruments. This makes us one of the largest user research communities among the country's 17 national laboratories. Argonne currently houses 6 user facilities on our campus, and they are funded by the U.S. Department of Energy. Tonight, we will explore 3 of our busiest user facilities. First, the Advanced Photon Source, what we call the APS, produces some of the brightest X-ray beams in the world. Those X-rays enable scientists to understand the structure and behavior of materials all the way down to the atomic level. In addition to contributing to 3 Nobel Prizes in chemistry, data from the APS has been used to make breakthroughs in longer-lasting batteries, breakthroughs in microelectronics, and many more research areas and endeavors. The Argonne Leadership Computing Facility, or the ALCF, houses our world-class assembly of supercomputers, which provide rapid data analysis and computing. At this facility, we recently completed building the Aurora supercomputer, which is the first AI-enabled supercomputer, making it the fastest in the world, or among the fastest in the world. The ALCF has also a Nobel Prize to its credit, and this facility is helping us keep the United States at the forefront of computing leadership. And the third user facility we'll discuss tonight is the Center for Nanoscale Materials, while using cutting-edge instruments like AI-guided robotic systems and unique electron microscopes to explore the tiniest particles and elements. Experiments here reveal the microscopic structure of materials, which enables innovation at the smallest scales. And these user facilities all work together in a tightly connected ecosystem. Each of them supports the other to accelerate interdisciplinary research. That includes end-to-end research workflows that span discovery, measurement, and analysis, and we do all of that here on one campus. They multiply the impact of science and enable discoveries that benefit society. Argonne is one of a handful of national laboratories where this type of integration and ecosystem exists. So joining us to talk more about these extraordinary facilities and the incredible innovation they're driving are some exceptional Argonne researchers. With us is Connie Pfeiffer, User Program Manager at the Center for Nanoscale Materials, Stefan Vogt, Associate Director of X-ray Science at the Advanced Photon Source, and Katherine Riley, Director of Science at the Argonne Leadership Computing Facility. Now, as you listen to our researchers, I want you to be thinking about questions that you may have about our user facilities, because we want you to engage with us during our question and answer session a little later in the program. But let's go ahead and get right down to business, right down to fun. Spring up Ms. Pfeiffer, get right down to the Argonne Center for Nanoscale Materials. Connie, please. You're welcome.
All right, let's go ahead and talk about nanoscience. My name is Connie Pfeiffer, and as Sean said, I'm the User Program Manager at the Center for Nanoscale Materials, and I'm so excited to be able to talk to you about nanoscience and all the work we do at the center. So nanoscience, what is it? It is the science of the incredibly small. The nano in nanoscience refers to a nanometer. So a nanometer is 1 billionth of a meter. So if you have a meter stick and you slice it into 1 billion pieces, each of those pieces is going to be 1 nanometer. To kind of help you get a scale of this small size, a piece of hair, it has a width of 100,000 nanometers. So when scientists are studying at this small scale, they're actually studying atoms and molecules. And to study these atoms and molecules, you need especially specific specialized equipment. And that is where the Center for Nanoscale Materials plays a vital role. The CNM is actually a part of a network of user facilities called the Nanoscale Science Research Centers. These are open to scientists across the country, and the mission is to advance scientific discoveries in nanoscience. There are 5 of these facilities located at DOE national labs across the country. Each of them has their own unique strengths, but together they form a collaborative, world-leading network. Since 2007, the CNM has been at the forefront of discoveries in nanoscience. It has made advancements in quantum information sciences, artificial intelligence and machine learning, microelectronics, energy, and medicine. It enables scientists to conduct high-impact research projects in order to develop new materials and learn about their properties. CNM scientists also conduct their own research, and they try to form large collaborative networks of scientists across the world. Over the last fiscal year, we welcomed over 1,000 users to our facility. While most of these users have come from universities, 30% of our users actually come from Argonne itself. And they come to access over 160 state-of-the-art tools and capabilities. And these tools and capabilities are in 4 main categories. We have synthesis tools, and these tools are used to create new materials. We have characterization tools, and these tools are used to analyze the behavior and properties of new materials. We have fabrication tools, and these tools are used to build devices and structures out of the synthesized materials. And then we have theory and data. So these are computational tools and software used to create models and simulations to help us predict the behavior. All right, now that you guys are experts in nanoscience and the CNM, let's get into the science of it. Over the last couple years, CNM scientists and users have developed a new qubit platform for computers, specifically quantum computers. Quantum computers can perform complex characterizations and calculations much more quickly than regular computers. Katherine will tell you a little bit about calculations in a little bit, so stay excited. So regular computers, they use information units called bits. These bits are typically represented by 0s and 1s. You can think of this as a light switch. It's either on or it's off. Qubits are the basic units of information for quantum computers. They can be 0, 1, or they can be a combination of 0 and 1 simultaneously. So unlike an on-off switch, qubits are more like a dimmer, where the light can be on, off, or any combination of on and off at the same time. So what did these scientists do? They wanted to freeze neon. So neon is a gas. They wanted to freeze this on top of a superconducting chip. And in order to do this, they needed really cold temperatures. So they used a tool at the CNM called a dilution refrigerator. A dilution refrigerator can get to temperatures colder than outer space, which is about minus 450 degrees Fahrenheit. I would not want to winter out there. So they took the neon, they froze it on top of the superconducting chip. Then they took a light bulb filament and sprayed electrons, and they were able to trap a single electron onto the surface. So this new tool gave the scientists an environment to control and manipulate these qubits more efficiently. So this gave them a way to explore new processes in technology and security and energy. Okay, another area of research is combining automation with AI or artificial intelligence to help accelerate discovery. Now at Argonne here, we have a couple autonomous discovery laboratories, and the one at the CNM is called Polybot. Polybot combines robotics and AI. AI helps Polybot think about experiments and how to conduct them, while machine learning helps process the information around the clock. Okay, so automating this process really helps our researchers. It helps free up their time so they can spend their efforts interpreting the data and coming up with creative solutions and problems to ask next. We are very lucky here at Argonne, you're going to hear this multiple times today, that we have several user facilities in one location. This makes us use all the capabilities for one project. So for Polybot, we made some thin films. These are very thin coatings you can put on surfaces and put electronic devices in them. We built them, and then we were able to take them to the APS to use their X-ray imaging capabilities to help us determine the structures of these devices and their properties. Okay, and then one final example. We have a multi-facility team developing a software program called Digital Twins that will help scientists who come to use our user facilities. In this example, digital twins are virtual models that simulate real-world research environments. This means that this helps scientists practice before they get to our user facilities. When you use a user facility, you're given a certain amount of time to come to that facility, and that amount of time is usually very short. So you have to make sure that you are very efficient in your experiments. So this program will let scientists actually practice, learn what parameters they need, what kind of data they're going to get out of their experiments before they actually set foot in our facilities. So when they do come here, they are prepared and ready to go. They're not going to be wasting any time. And this work is absolutely not possible without the three of us together. It takes the CNM, APS, and ALCF to help develop this, enabling scientists to have smarter planning and more efficient results. Now, the future of the CNM is really focused on discovering and engineering new nanoscale materials in areas like quantum computing and microelectronics and next generation computers. We really are trying to emphasize learning about tiny defects and how we can manipulate them and use them to make more reliable devices for computers, for electronics, for batteries. And we're really trying to speed up the discovery of these new materials. And to do that, we're taking the CNM capabilities and pairing them with the APS, their X-ray capabilities. And speaking of APS, it's my pleasure to introduce our next speaker, Stefan, who will tell you all about it.
Thank you very much, Connie. And first, I think we need to give a very nice round of applause for Connie because she's done a wonderful job. So I'm Stefan. I'm Associate Division Director in the X-ray Science Division at the Argonne at the APS, and I'll tell you all about what APS is about. So similar like CNM has 5 different facilities in the DOE complex, we actually have also 5 light sources in the DOE complex. And we at Argonne are the largest source, so our circumference is about 1.1 kilometer, about 0.7 miles, so sizable. What sets us apart is we're doing mostly hard X-rays. So if you're trying to do X-rays with an energy between 5 and 100 kV or so, we're just the best source, not just in the US, but currently worldwide. In terms of energy, that compares to, if you get a medical X-ray exam, that might be the kind of energies that we would use. And with that, you can look deep into material and study these while they're operating. By contrast, facilities like the Advanced Light Source in Berkeley, they use soft X-rays. Soft X-rays are great if you study surfaces, for example. So APS in a few numbers, we have about 72 X-ray beamlines. So that's how we call our instruments. These are essentially end station instruments that are after about 70 meters or so of a vacuum pipe. And we use these X-rays. One of these beamlines actually run collaboratively with CNM. So we actually jointly operate one of these. We have something like 5,500 users that come to us every year, typically from academia, but also from industry. About 2,000 students, 1,000 postdocs. So it's quite a bit of an impact. Something like 6,000 experiments that we carry out every year, which result in 2,000 papers that our colleagues publish together with us. And overall, a large number of societal impacts. Sean mentioned there were 3 Nobel Prizes that included work at the APS. The most recent one was from David Baker, who got one for predicting protein structure just based on sequences. And we'll talk in a moment about why structures are important. So how does the APS actually work? Think of it as a gigantic X-ray machine. So on the animation, you see the start sign. This is where we actually inject electrons and then accelerate them to very close to speed of light. So think in the end, something like 99.999 and a few nines% speed of light. We don't actually use these electrons. They keep on circulating, like you can see in the animation. And as they pass through magnetic structures, what they do is they emit X-rays. And those are actually the things that we use. And I think there was a problem with animation, but it worked out okay. So I told you we're sort of the best source. What does best mean? We're the brightest. So here you can see a plot that shows the brightness. So at the bottom, this is a typical doctor's X-ray machine, thinking like going to the dentist. We had an upgrade recently. Previously, we were 1 billion times brighter. Now we are 500 billion times brighter than X-ray source in the lab. So what does brightness mean? Brightness means how many X-rays do you get into a small spot? And that factor of 500 billion allows you to do things that you just cannot do in any other way. And that really sets us apart. So I mentioned the upgrade. The upgrade actually was a very big project, 815 million. We're extremely grateful to our sponsor, Department of Energy, and the taxpayer that they funded this. And it has made us the brightest synchrotron light source in the world, right? And what may be rare these days, we delivered it on budget and on schedule, which is very nice. So what did we do? You see the image, new storage ring. Essentially, we ripped out about 1.1 kilometers of vacuum tubes, water cooling, magnetic structures, and replaced it with a completely new set. And what that allowed us to do is to change the beam from the old APS beam, which is like a pancake, to something that's very round and very small. And that allows us to focus it into a much smaller spot. What you see in terms of a picture there, first electron beam, this is our division director, accelerator science division director, Vadim, when he got the first electron beams in the ring to circulate. We had simulated everything, we knew it would work, but it's still a relief when it actually works. Not only did we replace the storage ring, we also got about 9 new beam lines, so completely new instruments, which allows us again to advance state of the art and go towards, for example, applying it to nanoscience, but also larger scale projects. So what do we do in terms of science? We have a very wide range of science. I think Sean mentioned battery materials. So you see a coin cell, right? And what you can do is not just look at the coin cell in transmission, but you can actually look at it while you're charging or discharging it. So you learn how to make better battery materials so that your batteries, if you charge, goes through more charging cycles, for example. We also do quite a bit of work in material science. So think about, a screw. How does it fail? Trying to understand that really on the microscopic level as it breaks is something that's uniquely enabled by the APS because you can look at the fine structures as they go apart, for example. We do quite a bit of work in earth sciences, high pressure environments where you want to understand how does materials behave at the center of the earth, or for example, search for new superconducting material. We're also collaborating a lot with other divisions here at Argonne. So on the top right-hand side, you see a fuel spray. It's labeled combustion. So basically, think about the nozzle in your car that injects fuel into the motor. This is where collaborating with one of our divisions here, or directorates, where they're trying to simulate this so that you can build a car that's much more fuel efficient, meaning you have to pay less at the pump, which I think we all want. And then bottom right-hand side, we do quite a bit of work in the life sciences. So think about, for example, trace metal imaging. This is looking at iron, copper, and zinc in a zebrafish embryo, and people try to understand what is the role of these trace metals in living organisms. Just a few highlights. So this is looking at structural biology. You, of course, remember COVID. You know, how can one forget the pandemic? Normally, we go through a number of maintenance cycles. What actually happened is when COVID came, we did not shut down. We minimized our maintenance and kept the main machine running, and running pretty much exclusively for experiments where we tried to determine protein structures. The movie that you see is a reconstruction that was from data was generated by one of our groups of one of the proteins within that virus. And you can see, if you squint maybe a bit, there's a green dot and a blue dot. So that is a medical compound that binds to that protein. And this is how you try to find drugs. You identify compounds that bind the protein and basically make it not work. And thereby you kill, in some sense, or make dysfunctional the virus. And work done by IMCACAT, which is one of the partners that help us run beamlines here, which is an industrial cat, an industrial consortium of users, dated measurements that allowed Pfizer to develop Paxlovid, which is one of the main medications against COVID-19. We also do completely different work. For example, here, this is an additive manufacturing. So think about 3D metal printing. Here, what you see in the animation is there's a metal powder, typically aluminum, tungsten, titanium. You melt it with a laser beam, and you see it's a fairly messy process. Particles are flying off. You can see sort of an empty void being created and solidifying again, and then there are bubbles that are being left behind. Those bubbles make the material less strong. So you really want to understand these processes to make the whole thing much better, and you can print whatever you want with a stability that is better than existing materials, for example. Here's some other work. We do a lot of work looking at imaging. So this is looking at an integrated circuit. So think about, a computer from a few years ago. It's actually a 60 nanometer FinFET device. So 60 nanometer means, in this case, that the transistor the size is sort of 60 nanometer. So on your fingernail, you can probably fit about 5 to 10 billion of these transistors. And with our X-ray machine, what you can do is you can zoom into that chip and extract the 3D data, and then really go across and delve into that data set to try to understand how are things lining up. Is the process working right? So industry is really interested in this for sort of early development of new processes. And I should mention this animation was actually done by the Leadership Computing Facility. I first tried to do it on my laptop, but the data sizes were too large and it crashed. This is about 4 DVDs worth of data. And you can see as you zoom out, you get a sense of the scale. It's all 3D and you can virtually deconstruct it. And this looks a little bit like hieroglyphs, which is funny, I think. So I think overall, the future is extremely bright. For us, we just had an incredible upgrade that improved our already bright source that we had in the past by more than 500 times. And if you think about the advance, it's like changing from learning how to fly to being able to go into space. That's actually a factor of 500 difference in speed. And so for us, it really helps us do new things in science that we couldn't do before. This is just one example of something that I'm personally really excited about. So what you see on the left in the grayscale image, this is just a sort of tomographic, think about CT scan image of a mouse brain. We are planning with the upgraded APS to be able to do this at a resolution that allows us to see how individual neurons are connected across the whole brain. So individual nerves connected. And the reason why we're interested in that is things like mental health research, things like neurodegenerative diseases. Understanding how the brain is wired is crucial for that. The brain is the least understood organ. At the same time, not only can we see these structures, but we can also see trace metals. So what you see on the other side in sort of orange, that's a map of phosphorus, not in the same example, but in a different one. And you can see, for example, gray matter versus white matter. And what you see in green is a distribution of copper. So copper on the one is a critical element, right? It's a trace metal. Without copper, we can't actually function. It's required, for example, the growth of new blood vessels. At the same time, it's toxic. If you've got too much, that's very unhealthy. So where you see these spots, this is where the blood-brain barrier is. We don't know why the copper is there. What is the function? Is it detoxification? Is it required? We just don't know. So with the new APS, we really plan on studying this a whole lot more. The data size, however, become enormous. So for that kind of resolution that would be required, you would need a stack of, the data is as much as a stack of DVD, roughly the size of Willis Tower. And as a single human, you just can't analyze that data. But we've got the Advanced Leadership Computing Facility. And with that, I want to give it over to Katherine Riley.
Thank you. And a round of applause for Stefan. Thank you. All right, hi everybody. Indeed, I am Katherine Riley. I am the Director of Science for the Argonne Leadership Computing Facility. I was one of the original hires in the facility when we started about 20 years ago. And I'm kind of excited to talk to you tonight. I'm going to talk to you basically what I've spent my 30+ year career doing, which is building supercomputers, but for science, right? How can we build supercomputers and make them really effective for science? One bit of history that I think gives us some good context here is that the lab has a long history of building computers in order to help with solving science problems. So they were building some of the first systems in the 1950s, and the driver for this was science we could not solve. And to take even a step further back from this is when you think about how a researcher wants to study a problem, they model it with math, right? So fundamentally, math is the language of science research. And when you think about that for a second, it's an equation, right? You know, it's some stuff equals some other stuff, like it's Schrödinger equation, or force equals mass times acceleration, or the Navier-Stokes equations. Some of these I think you probably would have heard of, and if not, forgive me. But some of these are straightforward. Sometimes you write down an equation and the answer is awesome. It's 42 and you're done and you can move on. Sometimes it's not, right? Sometimes the answer is complicated in and of itself, but also sometimes you just cannot write down an answer, or we can't write down an answer yet. That's a fair statement. And this is where computers come in, because they allow us to study these models of our universe that we've created where we can't just solve it on paper. And that's what was driving things originally. And the other bit of history is that the leadership computing facilities were actually founded by an act of Congress in 2004. The act, the High Energy Computing Revitalization Act, which always makes my tongue trip. I really want to mispronounce this one. But it commissioned the DOE to build 2 leadership computing facilities, or to build a leadership computing facility, which became 2, one here at Argonne and our sister facility at Oak Ridge. And the driver behind this was recognizing that in order to lead in science, you need to actually deploy world-class instruments. So there's world-class instruments in the CNM and the APS, et cetera, but it was the recognition that actually a world-class computing capability was needed in order to be a leader in science. And the other exciting component to me for this was that the leadership computing facilities were explicitly open research facilities. That means that anyone can apply for time and compete for that time. You have to compete, you don't just get it, right? You do have to compete, but anyone is open to apply. And that work, the only thing you need to do in order to be, to successfully get that is to openly publish your research. So all of this would be open research. Now, over the course of our 20 years, we have deployed several flagship systems, but the current one we have on the floor is Aurora. And I kind of skipped over something earlier that I want to touch on, right? So the power of these systems is that they are incredibly flexible scientific instruments, right? What that means is that the only constraint really is what you can, your imagination to some degree for what you can run on these. What kind of problem, what kind of science you want to do, what kind of experiment you want to run. You just need to write the software to execute on these systems. I laugh a little bit at myself too, because that's what I did for most of my career, is write these software. It's hard, but that's what's so powerful about these, any field of research. Now, Aurora is big, and there's a lot of reasons it's big, and I'll come to some of those in a few minutes, but to give a sense, it is about the size of 2 professional basketball courts. It is made up of over 10,000 nodes. So what does that mean? Your laptop, for example, or even at this point, your phone, really is, you can think of it as it is a computer, right? If you take off your keyboard, you take off your screen, you have inside your laptop, you have CPUs or GPUs, probably both these days. You have some memory, you have networking, right? Ability to talk to stuff. Aurora is basically a bunch of those nodes. Each node, though, is about this big, weighs about 70 pounds. It has immense capability, even in one of those nodes, and there's over 10,000 of them. And I'll also say that Aurora does not stand alone as part of the ALCF. It is actually surrounded by a breadth of other world-class capabilities in both data and networking. It allows us to do things like talk very quickly, not just say CNM and the Advanced Photon Source, but even to other facilities that are around the world. And all of those things have to work together to make the kind of level of tool that Aurora is for science, the level of instrument that it is for science. So similarly to what Stefan was talking about, here's just some basics of what the ALCF does and the breadth of what we do. So Aurora really, in any of these types of facilities, but Aurora can work on problems that are as small as thinking about subatomic particles and the fundamental structure of matter. It has worked on problems where we're trying just to design a better concrete, right? You might think, really? But yes, concrete, very hard problem. It has worked on problems where we're trying to take billions of possible compounds that could be used in drug design and bring them down to maybe like 100, so we could do those in a lab instead of trying to work through our intuition, right? That's a huge improvement, right, in terms of time to a drug design. And it, of course, works, this is very close to my heart, on problems that are things like, how do stars explode? How do the stars function? How is our cosmos structured, right? How is it evolving? But it really touches on all fields of science. I have failed in my time to find an area of science where it has not touched in some way, shape, or form. And that, again, is I think one of the powers of Aurora and the ALCF as a scientific instrument and facility. I wanted to touch on a few examples, still pretty high level, right? But to give you a sense of the scope, right, of how a problem might get tackled on one of these systems, right? As I mentioned, remember, all of this things kind of comes down to equations, right? We're just trying to solve equations, sometimes just a lot of them at once. But one of the types of problems is battery design, and we've already heard about this, right, from CNM, and how this is done at CNM and how this is done on the APS. And a lot of that work actually is supported by resources at the ALCF, but also done independently. And so we will work on problems that are trying to make, what's in your pocket or perhaps your hand right now, that battery more effective, make it longer lived, make it less likely to explode in the overhead compartment on airplanes, and generally improve sort of our relationship with portable energy, right? So how can we save energy for when we actually need it rather than when it's being just generated? And we work on that from the smallest scale. What we might be looking at really on the atom level, how a battery is built and how all of the different parts of that are working together, how on the atomistic scale we're even storing energy, but also looking at the holistic battery all the way up to saying, okay, I have a whole device here. And with that whole device, how can I manage defects, right? So if I have this much, this many defects within my battery, when does the battery become unreliable? When does it become unsafe? When can I really, accept that this might be, a reasonable level of imperfection? But also, what alternative materials can I use in the battery, right? Are we going to use lithium-ion batteries forever? No. What alternatives can we find? And that's the type of work that we're really focused on batteries. This is over dozens of projects. The second example I wanted to give in terms of sort of big picture ways that people use large-scale computers is engine and aircraft design. And the reason I love this example is this is a field of research where our confidence in the models, so this is the stuff that runs on Aurora, our confidence in those models is so high that even our industry partners like a GE Aviation and Boeing, when they're thinking about new engine designs and new airplane designs, their confidence is so high, they use these tools as their primary design tool. And they will be able to run through thousands and thousands of ideas instead of a few on their desk, right? Just take it to the extreme. But think about that, think about the creativity you can get in your design, right? When you are able to kind of come up with an idea and iterate and explore with that on a computer rather than perhaps have to spend millions of dollars on building a prototype. And this has allowed incredible innovation in not just the fuel efficiency of the engines. As I trip, I was warned not to, and I did it anyway. But not just the fuel efficiency for engines, but even think about the structure of the plane, the shape of a wing. All of those things play together and result in more reliable and safer aircraft. And the last example I wanted to talk to and put it in context of computing is directly related to what you just heard about the brain. But here's why this one is different. We have a model for an aircraft. We have a model for an engine. We have a model for batteries and how molecules work. We don't have that same kind of model for a brain. And so the way you build the digital twin of a brain in order to do things like study how diseases progress, how we age, how you can treat disease, is by building up a model through experiment, taking these incredible slices, these incredibly thin slices, like you just saw, bringing them over to the ALCF, bringing millions of them, huge amounts of data, right? And using that to build a 3D model. So you're building your model out of data rather than as sort of out of the math, as sort of the, as I was describing at the beginning. It's a very different way of doing work and something we're going to see, I think, more and more as we move into the future. And my last comment is I kind of crack up at this phrase every time. Science is changing. Well, science always changes. It's never the same. Every single day, really, in the world of science, it changes, and that's its point. Right? The point is we ask a question, we might figure out the answer, or we get somewhere in answering our question, and we come up with 1,000 more. And the way that Aurora was designed originally was to try to tackle some of the big changes that we saw coming in science. We knew that the kind of questions that researchers were asking were getting more and more complicated. That's the nature of the business, right? When you always are asking another 1,000 questions after the one you've just answered, right? You want more answers. But also that the amount of data that scientists were collecting was getting huge. So not just data that's coming off of perhaps simulations we're running on Aurora, but data that people want to make sense out of coming out of places like the CNM and APS or coming out of observatories. These experimental facilities are generating data that we as humans cannot digest fast enough. So the future for the ALCF is really these considerations of how we bring these huge streams of data, the kind of computation that we need, and sort of an infrastructure that can support how you ask questions when you're integrating all of these things together. We know that when we designed Aurora, we designed that thinking ahead. We have an incorporation of that idea of incorporating data and computation, but also artificial intelligence is a next really powerful tool for how scientists are able to tackle big questions. But I think you will see even bigger changes in how we build systems and how we tackle these science questions over the next 5 or 10 years. As frankly, you'll see big changes just from even how AI is making us ask questions and enabling us, but how quantum computing, going back to Connie's talk, is also going to really evolve the way that scientists are able to ask and answer questions. Thank you.
Wow. Let's please give Katherine a round of applause. I learned even more about Aurora and our supercomputing capability here, and I really love the history lesson at the beginning and really the reminder at the end. Science is changing, it's evolving, and researchers here at Argonne are helping with that evolution. So we really greatly appreciate Connie and Stefan and Katherine for sharing their impactful work with us tonight. And we're also grateful to them for demonstrating how Argonne's user facilities work together to really benefit humanity. So please join me in giving all of our speakers a round of applause. Now, on to a little bit of fun. We want to see actually how much you were paying attention. How much did you learn from our lectures this evening? So time for a pop quiz. We're going to bring up our quiz host, Chris Gordon, and Argonne folks, you cannot play. Over to you, Chris.
Thank you so much, Sean. Hi, hello, everyone. My name is Chris Gordon. I am an internal communications project manager here at Argonne, and I was promised I'd get to use all the user facilities, but I guess I won't tonight. So I'm very excited to host this game show because everybody loves a test, right? So what we're going to do is play Argonne Unlocked Live Winners and Users Edition. Some of you came up, got a button, and put your name in a bowl. That meant you were signing up to play this game if your name was called. So we are going to pull your name out, and when your name is called, please come up on this side of the stage, and we'll get you seated. So contestant number 1, that's a blank one. That's a blank one. We've got Dave Cloak. Yes, Dave, come on up. Contestant number 1. Contestant number 2 is that Barb Harper? Barb? All right. So we've got Dave and we've got Barb. And contestant number 3, Wendy Klusendorf. Come on down to the stage. Get ready to be tested on Argonne Unlocked Live Winners and Users Edition. Wendy, come on up. You'll be contestant number 3. You can sit right here.
Where's Barb and Dave?
Here's Dave. You're contestant number 1. You can sit right here.
Center stage. Yep.
And Barb, take your time. No worries whatsoever. No worries whatsoever. Take the seat in number 2. Well, while we're waiting for Barb to come up, Dave, it's really nice to meet you. Tell me, where are you coming from tonight?
I come from north side of Chicago.
North side of Chicago. And if we learned a lot about different sciences today. Which is the one that you like, if you had to come and study science at Argonne, which one would you study?
Brain science.
Brain science. Yeah, I told them to make a digital twin of my brain, and they said no. Hi, Barb, where are you coming from tonight? Homer Glen, welcome. And what about you? Which science is the one that you really, drives you? The photon accelerator? Yeah, definitely. And Wendy? And material science. Well, welcome everyone. Round of applause for our contestants. What we're going to go ahead and do is we're going to go over the rules of the game. Is everybody ready? You've all got a microphone right next to you. So when right on the other side, there you go, and just speak into there. So here are the rules of the show. So each one of you will get 3 turns. We're going to do 3 rounds, okay? The players, you must select a category and a dollar value to reveal a question. Okay, you're going to get 10 seconds to pick the correct answer. This 10 seconds isn't going to start until after I read the question and the choices. It's multiple choice, so you've got a better shot there. The correct answers are going to earn that player the amount of dollars shown. I do have to say, because we're taxpayer funded, it's not real dollars. You're not getting real dollars tonight. The player who selected the question can answer, so don't yell out of turn, okay? And nobody yell out. You can play along here and online, but please don't yell out the answers, right? This is high stakes stuff right now. There's no penalty for incorrect answers like Jeopardy. You're not going to owe us any money at the end of the day, so don't worry about that, right? Do your best. And the player with the most points or dollars at the end will win some prizes, okay? All of the answers, correct answers, were discussed in tonight's presentation. So hopefully you were paying attention. I wasn't paying attention at all. Are you all ready to play?
Yes.
Okay. All right. Well, we've got going number 4, Dave. Pick any category and dollar amount from the board.
I'll pick the ALCF.
The ALCF for how much?
For 1,000.
We're gonna start 1,000. All right, let's see what we've got. What does the acronym ALCF mean? Is it the A, Advanced Linear Computing Framework, B, Autonomous Local Cloud Facility? Is it C, the Applied Large Scale Computational Facility? Or is it D, Argonne Leadership Computing Facility?
D, the Argonne.
D, let's see if you're right.
Computing.
Oh, the audience knows. The audience
thank
knows.
you.
D is the correct answer. 1,000 fake dollars to you so far, Dave. You're in the lead. All right, we're going to go over to you, Barb.
I'll take the ALCF for 2000.
Ooh, big spender. All right. What devices are used in the ALCF that foster breakthroughs in science and technology? Is it A, telescopes? Is it B, satellites? C, typewriters? Or D, supercomputers?
D, supercomputers.
D, supercomputers. Barb taking the lead with $2,000 in round one. All right, Wendy. Category and dollar amount.
I'm going to change it up with like the CNM for 2000.
CNM for 2,000 to tie it up. Let's see. Approximately how many nanometers are in 1 meter? Is it 1,000, A, B, 1 million, C, 1 billion, or D, 47?
That'll be C.
C, 1 billion. Oh, we've got another correct answer. I'm going to go now. I hope you're keeping track of the scores at home.
Yes.
But we have an official scorekeeper here, Danielle Toasty. What's after round one, where do we stand?
Yeah, it is close. We got Dave with 1,000 and Barb and Wendy tied with 2,000.
Okay, well, Dave, that should go into. I know that you're not a supercomputer, but what do you want to go next to kind of stay in the running here?
I'm going to go for 5,000 on the APS.
5,000 on the APS challenge. The gauntlet has been thrown. Approximately how much did the 2024 APS upgrade project cost? Was it A, $815 million, B, 3 Bitcoin in a rocket, C, $81.5 million, or D, $500 million?
D.
D, $500 million for $5,000. Is that correct?
Oh, it's 81.
$815 million. Well, you were close. I think that's how much 3 Bitcoin in a rocket costs.
Yeah, I was going to say the Bitcoin.
That was a trick question. Well, moving on to Barb.
I'm super competitive, so I'm going to go for 5,000 for the CNM.
CNM 5,000. What does a digital twin mean when referring to CNM? Is it a robot that replaces scientists? Is it B, a physical copy of a laboratory? Is it C, a virtual model that simulates real-world research environments? Or is it D, a cloned researcher working overtime?
That would be C, a virtual model.
C, a virtual model. I can't even keep track of the scores anymore. But that was a 5,000, Wendy. What are you going to choose?
I have to keep up. I'm going to have to go with 5,000 for the ALCF.
5,000 ALCF. In brain mapping research, what does a digital twin allow scientists to do? Is it A, replace doctors, B, study how diseases begin and evaluate treatments, C, replace traditional MRI machines, or D, create a roadmap for cars?
Going with B.
B, study how diseases begin and evaluate treatment. Wow. All the high dollars. Dave, I don't know how we're going to do this, but we're going to find out. After round two, where do we stand?
All right, Dave still at 1,000 and Barb and Wendy neck and neck, 7,000 each.
Oh, tied at 7,000. Thank you. Well, Dave, what do you want to go for?
I'm going for the CNM.
CNM?
Of 3,000.
3,000. All right. About how many users come to CNM each year? Is it A, 500, B, 1,000 plus, C, 150, or is it D, 25,000 intergalactic researchers?
I should pick D, but I'll take B.
B, 1,000 plus. That is the correct answer for another $3,000. Just remember, I'm not giving you any money, Dave.
I know,
Just
I know.
Remember that. All right. Well, the two tied. Barb, what do you want to go for?
I'll do the ALCF for 3,000.
Okay, big choice. Okay, which of the following best describes how ALCF modeling supports improvements in aircraft and engine design? Is it A, safer, quieter, and more efficient? Is it B, bigger and heavier? Is it C, faster and cheaper? Or D, is it more hamster power?
I'll have to go with A, safer, quieter, and more
A,
efficient.
safer, quieter, and more efficient is the right answer. Wow, 3,000. Barb, you're hitting 1,000 right now. Wendy.
I'm going to have to go with APS for 3,000 to keep up with Barb.
Okay. All right. Approximately how many unique users visit APS annually? Is it A, 55,000, B, 1,000, C, 3,000, or D, 5,500 unique users?
I think it's D.
Do you think or do you know? 3 seconds.
D.
D, 5,500. Is that correct? Whoa! Oh, my goodness. scores. I am not good at math. Danielle, Tosi, what are the final scores here?
All right, we have Dave at 4,000 and Barb and Wendy tied each with 10,000.
That's amazing. Well, here's the tiebreaker. You're both winners. Actually, you're all winners because this is the winners and users edition of Argonne OutLoud Live. Thank you all so much for playing. Round of applause for everyone. Please collect your prizes from my compatriot, Jeremy. And thank you so much. Thank you.
From you, our audience. It's time for our question and answer session. And our researchers, Connie, Stefan, and Katherine, are joining me back on the stage to take your questions about tonight's presentation. Before we begin, we would like to set a few ground rules. We ask that you direct your questions to our three speakers and that you keep your questions relevant to tonight's presentations, to their topics, which are user facilities. Please be considerate of time, ask only one question, and refrain from repeating questions asked by others. If you're here in person, please line up right here at the microphone station that's in the center aisle towards the back of the room. And if you have a question and you're joining us virtually, please type your question in the chat. So, if anyone's ready to line up, we'll take our first question. We have some folks traveling to the back. Excellent, please. Oh, and hold 1 second. We're waiting for the microphone to get turned on so our online participants can hear your question.
Hi, you touched briefly on AI, but it's moving at a logarithmic speed. So you're a government facility. How are you guys handling that? Are you going to move fast?
So the question is about us adopting AI and moving quickly. Maybe we'll start with ALCF.
Yeah, so I love the fact that you sort of phrased that with but you're a government facility, are you moving quickly? But I think that there's several good answers to that. So yes. The short answer is that the structure really of how science is happening right now is really built around, in many cases, tackling how effective AI technologies can be as a tool for science in answering that question. And frankly, I would say we're at like warp speed on trying to tackle that, right?
Yeah, warp speed.
And yeah, and I think there's a lot of other things I could say about it, but from a purely like sort of just internal excitement component, there are ways that this will game change the way we do science. And that's everything from how well the models we have run to reinventing how we might think about building entirely new models to even the way we as a scientist work on a daily basis. And so, yes, there's a lot of effort to move very fast.
Would one of our practitioners of AI, would any of you like to quick answer?
Working together.
Yeah.
We have to work together in order to handle the large amount of data that we're generating. And if we can't work together, then we can't make progress quickly. So teamwork.
Fantastic.
I'll just chime in. I'll second that. It's about teamwork. We've got Argonne is a fantastic facility, and you can see the speed with which we make progress. There's been teams of people that have, the image that I showed on the integrated circuit with conventional means reconstructing that takes us months. With AI, we've been able to speed this up to, hours. Yeah. So it just changes what you can do.
Yeah. Before we go to our next question, maybe I'll do a shameless commercial. I appreciate your point about government being slow. Thank you, Katherine, for doubling down on that. But hopefully you've heard about Genesis Mission, which is a new approach for government to move very rapidly, very fast. And Argonne is playing a pivotal role in this new endeavor of the Department of Energy, which they're getting other agencies to come along. And so I think you're going to see a new government moving much faster to really rapidly accelerate science. So we're very proud to be a part of that activity. So hopefully you'll learn more about Genesis mission when you go home. Let's take one more question here, and then maybe we'll go online. Please.
Yeah, good evening. Building on your comments on teamwork, this is for all three of you, can you provide one example where all three of your areas collaborated together to solve an issue?
Whoever would like to start.
I can come up with examples where like if I'm taking ALCF, CNM, and APS, I can certainly come up with examples, multiple examples where like ALCF and CNM we're working, and ALCF and APS we're working together. And so, I mean, as soon as I'm having a range fog all together.
Digital twins model
Yeah.
is kind of the first time, it's a really big first effort to work together as a team where we're generating images and data, and then ALCF is taking that to help model these future experiments and make these simulations where scientists can actually practice before they come.
And actually, sorry, you triggered, I think that's a really other good example of this. And it is a really deeply teamwork one. Over the course of the past year and a half or 2 years has been a very large effort within sort of, certain slices of the Office of Science to make basically create an ecosystem where it's even smoother for researchers using one facility to be able to use another, right? And so it might have been straightforward if you were using one compute facility to try to use another, but if you were using experimental facilities, how you could interconnect them all. So that's a really large effort. There's a whole lot of stuff technologically and socially that are challenging there. And it's a really, I think, an excellent example of teamwork. It's one that's crucial, right, for the digital twin idea, because you have to have different components working smoothly together at that point.
Excellent.
Thank you. Thank you.
Thank you. Do we have a question online?
We do. We have a question for Stefan. Are materials in the beamline heated, destroyed? What happens to them?
That's a great question. So typically, we reference X-rays as being non-destructive measurements. But if you put so many X-rays into a small spot, you do start to make damage at some point. So it does depend on the exact experiment. For some experiments, we do things on a scale where there's no real damage during the time that we measure them. We have looked, for example, at insects, and they were fine. But if you go towards the highest resolution, then yes, indeed, you start to get damage. And depending on the sample, it can be heat, and it can just be sort of structural deterioration.
Great, thank you. Maybe we'll go to the in-room question.
Oh, hello. I believe Katherine and Stefan and Connie may have addressed this question, but it's another kind of team-related question going about the social aspect. I just wanted to ask, what kind of management processes exist to help the teams evolve from simple early-stage collaboration teams to mature, high-performing teams that can deliver, groundbreaking science? I think you touched on some of them, so don't want to repeat it.
I can take this into a little bit different, where we haven't talked about yet, but we do a lot of social interactions together. I'll talk about the user side, where the APS and CNM are joined in a user meeting every year where we have our users come on site together to talk about the science they're achieving and doing, and try to get collaboration starting that way, getting scientists to talk about what they're doing, our staff talking about what they're doing, and hoping that they join together to create projects and come up with new fascinating ideas to follow through at both of our facilities.
Please, Steph.
I would add, one of the things is probably making just people aware of what else is going on around the lab. The lab is fairly large, and there's lots of really exciting work going on. You only saw a small sliver of that today. But if you get to connect people and they realize, oh yeah, I can use, for example, some of those resources or tools over there to further your own science, that really creates so much excitement that as management, sometimes it's the best thing to just go out of their way and let them go ahead and do research.
And I was going to augment this, but when I say sort of augments that, right, which is I think once you're able to find people and connect them, right, the structure of how we operate really is collaborative. I think that's one of the compelling components of the national labs is right there. They're designed to be collaborations. And so that might sound petty, but or not petty, but trite, I think, but it's really absolutely true, right? The way we operate is trying to connect the right people in order to let them kind of create, right? And so the structure of our teams within, the facility are actually structured that way, so that once we get the people connected, you are able to sort of really riff off an idea and get excited. But I do agree. I think one of the biggest challenges is making sure everybody's aware of it, right? It's hard.
Yeah, thank you for that. I think we will go to another question online.
All right, there's a question about how you can trust AI. How do you qualify its answers?
Excellent question, another AI question. I know, Stefan, you're doing a lot of experiments right now using AI at the APS. Maybe we'll start with you.
Very happy to. So there's a couple of ways. Now, one very simple way is, for some experiments where you still have traditional means, I mentioned, you can do a conventional reconstruction of some of the data. You simply compare them. And, if they agree, then, well, it's right. You can also play games where you use only half the data for one method and the other half for the other. And the results, if they agree, you have a good certainty that the result is correct. There's probably even further, I'm sure there's
Fantastic.
mathematical methods.
Yeah, and I think what's important to understand too is that in many applications of a different AI technology, right, we're still exploring and improving, right? And that's why you are doing something, right, by comparing the real data against what you might get out of AI, but also figuring out what those guardrails are, right? So that's an active point of research right now. I mean, it's a fantastic question because it's exactly, I think, what we're tackling, right? How do you put guardrails? How do you define, okay, when can I use this? When can I use AI? When should I not? When have I reached the limit? And an interesting point is that I think this is true of modeling and simulation as well, right? We're just more familiar with it. We've had more decades to play with it. But this is what we're doing right now with AI technologies. We're figuring out when and how and why.
Yep. Anything to add, Connie? Or?
Oh, those were excellent answers.
Yeah. I agree with you.
Yes.
We will go to another question in the room.
Thank you. I'm Harsh Kapula. I'm very interested in digital twins, which you spoke about quite a bit. They imply that the digital twin truly represents the behavior of whatever it is that you're making a twin of, an ecosystem, a jet engine, whatever it is. How do you know when it's truly representative enough to be able to do something with it and model or experiment?
Yep, great question. Connie, you introduced the notion of digital twins. You want to start and then maybe Katherine can...
It's at the very early stages with us, but as you collect more and more data, that's when you start to, you map, you see the trend, you see how it's fitting together. So right now we're trying to collect a large amount of data to get to the point where we can start seeing trends and start saying, okay, we're seeing it's matching the experimental. In order to do that, you need data. So we're at the data collecting stage.
Yeah, and I think that's exactly right. It's experience with it. So just like, again, I made this quip a second ago, right, that we've had more decades with modeling and simulation. So there's places where we have a lot of confidence in those models because we've had so many years of understanding how they perform and their constraints. And the same will be true for the digital twins. It's kind of echoing what I said before, that it's the really giving the time to be able to prove it. And in some fields, being able to prove that you have confidence in that twin will be much faster, either because you have a great deal of raw data, right, to compare against. Perhaps you have a great deal of, simulation background to compare against. But it is sort of the slow iterative process. And you start in any of these things using it within a very constrained environment, right? Or a constrained, application. And then you slowly test the boundaries and expand.
Great, thank you. I think I'm getting the signal we have time for one more question and we'll take that in the room. Please.
Hi, thank you for having me here today. My question is, do you think computer science can advance drugs through the FDA pipeline faster? And if so, how can the ACL help with that?
So without a doubt, right, there's been there's been multiple examples where we have been able to contribute a much faster discovery process. And it's something I alluded to, where you're really going down from, billions of possibilities, or perhaps, whatever, many, many possibilities, down to a very, very few that you can actually potentially deploy in a lab and experiment to see if they're effective. I think there's a component of your question I cannot speculate on, because, and I mean this sincerely, right? I have some sense of the complexity of the FDA pipeline, and I'm not going to pretend I can answer how much we could accelerate it through that. But I can say that we absolutely can accelerate the time to getting something there, right? Into the start of that pipeline and into trials. Yeah.
Great. Thank you for that. It's a different part of government. So
I do not want to pretend to be an expert in that one.
Yes, different part. I will take a very quick moderator's privilege and ask one final question and end on, very briefly, what's been your most exciting or favorite experiment or outcome at each one of your facilities?
Okay, I'm very excited to answer this. I'm going to go first. So part of the thing we didn't get to talk about today was the outreach we do at the center. So we don't only do science, but we try to educate everybody about science, and we try to really empower the next generation of scientists. So one of my very favorite programs here is called the Exemplary Student Research Program. And what it does is it takes local high school students and invites them onto our user facilities. They get to be actual users. They get to create experiments. They come work with our scientists. They write a proposal, even sometimes better than our actual users. It's amazing. And then they come and do the experiments. And at the very end, they get to show their work to the actual scientific community. They do a poster session at our user meeting explaining their work. And just the excitement you see with these kids is just so great. My kids were working with mushrooms. They picked mushrooms, they looked at them under the microscope, and they're still talking about it. Every week they're like, oh, I figured out why we saw chlorine in these. And it's just so fun to watch them get so excited on such complicated topics.
Love it, hard to beat. Think we're going to end on that? On mushrooms.
Good luck.
Yeah. Thank you so much. Let's really thank our panelists and our presenters. We too want to thank you, everyone here participating in our Q&A segment. Thank you for your really interesting questions. I know we couldn't get to everyone, but our presenters have been kind enough to agree to stay around just for a little while to answer additional questions at the end of the program, to talk to you one-on-one. Now, before we let you go, we'd like to direct your attention to the QR code that is on the screen, which will take you to a very, very quick survey with a handful of questions about your experience at tonight's event. We'd love to get your responses from both our in-person audience as well as our virtual audience. Your feedback will prove valuable when planning this series in the future. If you're interested in revisiting tonight's lecture, or you'd like to pass it on to someone else to learn a little bit more about Argonne and our user facilities, you'll find this program on Argonne's YouTube channel in about a week. You can also visit our OutLoud archive page on Argonne's website for the link. Thank you for joining us this evening. We hope you enjoyed your time, hope you enjoyed Jeopardy, and most importantly, we hope you really learned a lot about science and about Argonne. Please come back to join us for future OutLouds. With that, please have a safe evening. Thank you.